All right, so looking at this function, James, tell me one or two places that this function is not continuous.
-6.
Okay. -6, I agree. Where else?
5.
+5?
Yes.
Yep, I definitely see a jump right there. Ivan, what are some other places that this function is not continuous?
-10.
-10? Okay.
-4.
-4. All right. Ivan, talk to me about the -10 spot. Why is the function not continuous
There's
at
a hole.
-10? There's a hole. Okay. So function is not continuous if there's a hole. How would you put that mathematically? What is it? How would, I mean, is that a problem? That's a problem like.
Would it be like if f of a does not exist?
Okay, yeah, like f of a does not exist. All right.
Isn't the problem with saying f of a just f of a does not exist? Because f of a does exist, it just exists at 0.
That's true. If we're looking, you're talking about -10?
Mm-hmm.
Yeah, f of a does exist. It's right down there. So that's not necessarily the whole. What this would be a reference to, do we have any
It's like
spot where
11.
11, yeah, okay. So that's definitely a spot where it doesn't exist, f of a doesn't exist, okay? And we can definitely say the function is not continuous there, okay? This is kind of a special case, so maybe we should hold off on that. Is there another place where f of a doesn't exist? No, there's not right there.
Word just doesn't.
-4 doesn't exist because there's an asymptote. Okay. So a function is not continuous if like there's a hole. Well, not necessarily a hole, but we would say something like the function doesn't exist there. Okay. What about a +5? The function does exist at +5. Okay? But why is the function not continuous at 5?
The limit as x approaches from the left doesn't equal the limit as x approaches from the right.
Okay, yeah. So the limit as x approaches a from the left is not equal to the limit of f of x as x approaches a from the right. Okay. Now last week we talked about a situation when this happens, this is what we call the behavior differs from left and right. Okay? And so what this implies is that the limit of f of x as x approaches a does not exist. Okay? So it's a function is not continuous if the function doesn't exist at that point. The function is not continuous if the limit doesn't exist at that point. That's condition 1. That's condition 2. And then there's condition 3, which condition 3 is where we're going to look down there at -10. Because let me ask you this. Does f of -10 exist? Yep, it's 0. Does the limit of f of x as x approaches -10 exist?
Mm-hmm.
What is it, Ivan?
1.
Yeah, it's 1. Okay. So is the function continuous at -10?
Mm-hmm.
Okay. So what's the problem? The limit exists and the function exists.
But the function is not equal to the limit.
That's correct. The function, it does not equal to the limit. That's the third situation. That, namely, f of a must equal the limit of f of x as x approaches a. Function has to exist, the limit has to exist, and they've got to equal each other. Those are your three situations for a function to be continuous at one particular point. Now, once we say that a function is continuous at that point, then we can talk about a function being continuous on a region. Because we can say the function is continuous at all points from here to here. So we can say that every point from positive 1 all the way up to positive 5, each one of those points, the function exists, the limit exists, and the function equals the limit at each one of those points. All right? So three situations in which the limit doesn't exist. Now, three situations in which a function is not continuous. Okay? Now, if I were to scale it down, I wouldn't bother writing that. Limit doesn't exist at that point. This is how I read it. A function is not continuous at x equals a if f of a, hold on. I'll write this down. A function is continuous at x equals a if f of a exists, the limit of f of x as x approaches a exists, and those two things equal each other. This is your final answer. So there's three of those situations. Now, don't confuse these three with the other three. And those are the three situations in which a limit doesn't exist. And those are behavior differs from left and right, unbounded behavior, and oscillating behavior. Which we talked about those three last week. Those three deal with the limit, which is item number 2. So that leads me to our first blue sheet. Might be a good place to summarize that information.
Mr. Goddard?
Yes.
Where do I turn this?
I don't know if we've graded it yet, so just hold on.
Are we keeping this?
Yeah, you'll keep that document. All right. In order for you to be successful on the chapter tests and quizzes, there's some things that you have to have memorized. And I know exactly what those things are because I've seen what students have told me, and I write the tests and things like that. So before every test, the day before or earlier, we're going to have a memorization quiz over stuff you must know cold, stuff that you've got to know, okay? And for chapter 1, there are 2 blue sheets. There's that sheet right there, which says List the 3 conditions for a function to be continuous at x equals c. Well, what do you know? There they are right there. You can fill them in on your blue sheet. And then list the 3 situations in which the limit doesn't exist. And there are those 3 right there. Behavior differs from left and right, unbounded behavior, and oscillating behavior. And then the 2 special trig limits, which we talked about last week, those are on that paper as well. What I'm basically going to do is on Thursday, or Wednesday I guess it looks like, I'm going to give you a sheet of paper that looks like that, and it's just going to be blank, and you're going to have to write those things down. In addition to these things. This is the necessary algebra and trig that you'll need to know. Leave this here, that goes on the bottom of that. File here for Harley. So tonight, part of your homework is going to be fill out that algebra and trig chart, and come tomorrow. Let me know if you have any questions on any of those that you could not find the answers to. All right. So today we're going to finish. We're going to do some continuity problems right now. Tomorrow we'll talk about limits. Wednesday we've got a memorization quiz as well as a review, looking at some tough problems, similar to the ones you'll see on the test. Thursday is the test, and then Friday we'll start on Chapter 2, difference quotient. Now, the test on Thursday is going to be over limits. So, it's going to be multiple choice. Because we still don't have any other mechanism right now, it's going to be on paper. And you'll have a calculator available to you, but that's about it. Okay? And the way that this works with the tests is that if you don't do well on it, if you get lower than a 70, or in fact if you get any grade, I'll give it back to you and you'll be able to work on corrections on that particular test and then turn those corrections in. And I have a little correction form that says like, copy the problem down, copy the answer down, and then ask a couple of like evaluation questions. What did you do wrong? How are you gonna make sure you don't do this again in the future? If you do those corrections, you do that corrections procedure, turn that in, then I will give you some points back. And that's good for anybody, no matter what your score is. Okay? I don't curve the tests. Let me take that. I do curve the tests if you've done the corrections. That's the qualification. So you got to do the corrections, and then I get to curve it. But if you don't do corrections, then you're stuck with whatever. And just a heads up, the average score on my chapter tests is like the AP test score, average score, because that's where I pull the questions from. So the average class score is normally a 50, 60, or 70. Contrast to your normal, I mean that's 50 or 60 or 70s. That's about the average test score. That's what the average AP test score is. But that doesn't mean all failure. Normally 50s, 60s, and 70s would correspond to 3s, 4s, and 5s on the AP test. It's just they're really tough questions. So anyway, so I do curve it, but it's based on, yeah, I mean you can make like a 65 on the AP calculus test and still be okay. Because it's so tough. Okay. I'd like to do some of those problems together, or at least kind of set some of them up, if you are okay with that. All right, let's go ahead and look at that together. Go ahead and read through that first problem, see if you can. An answer on that. All right, James, read those instructions to us there for number 1.
Find the intervals on which each function is continuous.
All right. So, James, where do you think this function is continuous? Maybe I ask you a different way. Do you think there's any place where this function is not continuous?
The middle parts where it curves.
Right here?
Mm-hmm.
Okay. Yeah, possibly. That's kind of an interesting location right there. Let's look at that guy. Well, here's a question. Does maybe you want to look at, you're talking about like maybe 0 here or one of these other points?
Like 0.
Okay, we'll look at 0.
Or-
So here's my question. Does f of 0 exist?
Mm-hmm.
He says yes. Somebody else. Does the limit as f of x approaches 0 exist? Ivan shaking his head, yep, I agree. What is the function value there? James?
7.
7. Ivan, what is the limit approaching?
7.
7. So are they approaching the same thing?
Mm-hmm.
Or the limit is approaching the same thing as function value? Yeah, the function is continuous there at 0. If we look here, down here at this trough point, same sort of situation. Function value exists, the limit exists, and they equal the same thing. We might think, is there an asymptote here? Well, there's no dashed line to sort of indicate that. Plus, if we look at the function, it's a cubic, well-behaved function. Cubic is continuous everywhere. So, this says find the intervals on which the function is continuous. The answer is it's continuous everywhere. So we'll write negative infinity up to positive infinity. Now, Gracie, number 2 looks like it's going to have some problems with it, right? Namely, you know that the cosecant graph has asymptotes. Now, they're not shown here, but there's asymptotes, right? However, look at the function definition. Yeah, they're saying from negative pi up to pi.
So the only problem is 0?
Yeah, the only problem seems to be at 0. So if we're looking between negative pi and positive pi, where is it continuous? Well, or maybe we can say it's definitely discontinuous at x equals 0, right? So the way that we're going to write this is we would say it is continuous from negative pi up to 0. And then we could write union from 0 up to pi.
Would you do parentheses or brackets?
I'm doing parentheses because I think we're going to put parentheses on pretty much all these things. It's sort of like the general rule when it comes. It's kind of whether or not a function is continuous at the end point. But it is not continuous at 0 because the function does not exist there. So that's how we put parentheses with zeros. Yeah, you know what? It's also not continuous at negative pi by definition because at negative pi there's an asymptote. So that's the reason why we're not going to put something at negative pi.
Just 3 discontinuous everywhere.
Roger, you remember what kind of function is this on number 3? It's a parabola. What's that? It is a well-behaved function. Parabolas are from quadratic equations. Well-behaved, it's polynomial. Polynomials are continuous everywhere. go ahead and work together and as a table if you want to check your answers. Raja, if you want to come over here, you and Gracie can work together on these. We've got 20 minutes. Let's try to finish this up right now in class. And I'll check your work and give you some feedback on it. All right? Today we talked about continuity and when's a function continuous. James, go and kill that if you don't mind.